Let's try to prove that if a plus b is even, then a squared plus b squared is even. Now, in our discussion here, let's see, I don't want to be squaring things out because we know that when we square a plus b, we actually get a squared plus 2ab plus b squared. Actually, that might give a different alternative proof. But I'm going to try to approach this by cases. That's my intention in this video, is to do a proof by cases. So, what could be true about a and b? Well, a and b might both be even. If a and b were both even, then we would have a is 2k, b is 2k, right? Then a squared plus b squared would be 4k squared plus, 4k and 4l, plus 4l squared, because 2k squared is 4k squared and 2l squared is 4l squared. And this would be equal to 2 times 2k squared plus 2l squared. So if a and b are both even, then a plus b would be equal to 2k plus 2l, 2 times k plus l. So that would be even, and in addition, a squared plus b squared would also be even. So that's one case. How about if a and b were both odd? If a and b were both odd, then a would be 2k plus 1, b would be 2 times l plus 1, a plus b would be 2k plus 2l plus 2, and that's also even, 2k plus l plus 1. And what would a squared and b squared be? A squared and b squared would be, let's see, 2k plus 1 squared plus 2l plus 1 squared, 4k squared plus 4k plus 1 plus 4l squared plus 4l plus 1. Yep, lots of factors of 2 in there also, aren't there? 4k squared plus 4k plus 4l squared plus 4l plus 2, and that also has this common 2. 2k squared plus 2k plus 2l squared plus 2l plus 1. So that one is also going to be even. This will be even, this will be even. Now for the third case, we could also have, without loss of generality, we don't need to worry about generality here. We're not losing any generality if we say that a is even and b is odd, simply because both of these are dealing with addition and squaring, and since addition is commutative, we don't technically care about the order. So what would happen here? Well, in this case, a plus b would be equal to 2k plus 2l plus 1, but notice that that's 2 times k plus l plus 1, and that's odd, so that doesn't even satisfy the antecedent. So although that is technically another case, that's a case that we don't have to acknowledge because it's not going to fall into the cases that our claim is actually talking about. Okay, so with that information, with that discussion in the background, see if you can pause the video, you can even look at the screen and write up on your own on scratch paper a proof of the claim. And assuming you took a shot to try this on your own, let's come over here and do it together. Proof. If a plus b is even, then a squared plus b squared is even. Case 1. If a equals 2k and b equals 2l, then a plus b is equal to 2k plus 2l, which is equal to 2 times k plus l. Furthermore, a squared plus b squared would be equal to 4k squared plus 4l squared, which is 2 times 2k squared plus 2l squared. So in this case, both antecedent and consequent are true. So in this case, we have a true antecedent and a true consequent. Case 2, we already know where we're going. In fact, I'll say similarly, so that way my reader knows that essentially I'm going to be saying almost the same thing here. If A equals an odd number, 2k plus 1, and B is 2l plus 1, then A plus B would be equal to 2k plus 2l plus 2, 2 times k plus l plus 1, and also we'd have that a squared plus b squared would be equal to, remember all those pieces we got, 4k squared plus 4k plus 4l squared plus 4l plus 2, and these have a 2 that can factor out. So we'd have a 2 times a 2k squared plus a 2k plus a 2l squared plus a 2l plus a 1. Finally, without loss of generality, for case 3, say A equals 2k and B equals 2k plus 1. Then A plus B would be equal to 2k plus 2l plus 1, which is 2 times k plus l plus 1, which is not even, which is odd. So for case 3, we're essentially saying that we don't have to look at the case in which one is even and one is odd. And these 3 cases, thanks to the without loss of generality, mean that we have completed the claim by cases. MWO.